Okay, so welcome to this series, the joint seminar series with the Fields and the University of Waterloo. And it's my great pleasure to introduce the first of today's two speakers. This is Jacek Gondzio, and he's from the University of Edinburgh. And Jacek has a long history of important results in the area of well, I guess what he's going to be talking about today in using interior point methods for linear programming related problems, and especially for solving very huge, large-scale problems. So, Jacek, I'll give the floor to you. Please go ahead.
Great. Thanks, Henry. Let me just share the screen. Can you see my talk now?
Yes, I see it perfectly. Yes.
Great, great. It does not need to be increased, decreased, or something. It's fine.
It's fine for me. Okay for other people?
Yeah, that's good.
Yep.
Great. Well,
okay. And recording is on, I think. So.
Yes.
So thanks, Henry. Thanks everybody else who was kind enough to come and spend this 1 hour. It's always a pleasure to talk about something that we are working on. There is this general belief that what we work on is interesting. So I'd like to share a little bit of my enthusiasm for interior point methods with the audience of today's seminar. So I'll guide you through some recent advances in iterative solvers, which are used in interior point methods. And here's the outline of my talk. I will very briefly go through interior point methods. They were born in '84. I'll give a few key ideas, and but then we'll move to today's challenges related to interior point methods. And in particular, I would like to go beyond the obvious things, the textbook information on interior point methods. So I'd like them to focus on those 4 items. Right, 1984. If you read George Orwell, then you would have rather bad connotations with 1984. But actually, I have the most positive ones, and think like Frank Sinatra, that when I was 24, it was a very good year. This was because Karl Markov did come up with his paper, and it shook the area of optimization, because it was the first polynomial time, well, not the first after ellipsoid method, but the very competitive new polynomial time algorithm for linear programming. And when you think of it, it was by far a non-obvious thing to do, partly because it was using some kind of shocking mathematical concept. You take a linear optimization problem and you add a non-linear function to the objective. So it goes against the common sense, against the practice of mathematics, the centuries of practice in mathematics. We do something like non-linearizing the linear problem. Now, I'd like to very briefly say how this is done, although maybe the vast majority of you know it to perfection, but it will also set up certain elements for discussion later on. So let's do it for linear programming problems. This is an LP, the primal form and the dual form, well, joined through the Lagrangian. And here we have the optimality conditions for such problem. Optimality conditions require primal feasibility, dual feasibility, and complementarity, which either may be written component-wise, either xj or sj has to be 0, or we can write them in the matrix notation, placing vectors x and s on a diagonal of a matrix. So capital X is a diagonal matrix with vector elements on the diagonal. If we do it that way, with the vector e equal to all ones, we can write this xj sj equal to 0 for all j just in one matrix equation. That's a very basic element of theory for linear programming. But what comes with interior point methods is this beauty, which is the logarithmic barrier function, to be precise, a minus logarithm, which can mimic the inequality, because if we add such a function to the objective, we will promote x's which are bounded away from 0. So, in other way, we will promote satisfying this constraint. And it doesn't take long to realize that if there are more inequalities like this, we can embrace them all by doing this summation of logarithms and then minimizing the function, the minus sum of logarithms, which is equivalent to minimizing e to such a power. But e to the logarithm just produces the value of variable. So if we minimize such an object, it is equivalent to maximizing the product of variables. And this already clarifies the intuition of interior point method that maximizing the product of variables means we do not want any of the variables to go to 0 prematurely. We will try to keep all xj's far away from 0. Now, how does it work in LP? Well, you take the linear programming problem and you replace the inequality with the logarithmic barrier function with a parameter, the Greek letter mi here. And then you formulate the Lagrangian, so standard duality, and write down optimality conditions for it. The optimality conditions now involve this term, mi x inverse e, which of course comes from logarithm. The derivative of logarithm is 1 over x. So this x inverse is a diagonal matrix where on diagonal we have elements 1 over xj for the vector x. And it suffices to introduce a new variable s, defined like that, which is equivalent to saying capital X times capital S times the vector of ones is uniformly equal to mi times the vector of ones, to get these new optimality conditions where a perturbation appears on the right-hand side of complementarity condition. And we can see it here on page 8, the essential difference. These are the optimality conditions for the barrier problem, and here we have optimality conditions for an LP. The only difference is here in this right-hand side, which is a perturbed in case of interior point, in case of the use of logarithmic barrier, and does not ask for xj times sj to be equal to 0, like in optimality conditions, but allows it to be a small number. When I say small, well, we can start from arbitrarily large value of mi, but we will gradually squeeze it to 0, and that way we will force that this condition eventually, in the limit, will get very close to that one. So optimality in interior point methods is approached in a very different way. Is approached by convergence but by driving complementarity products to 0. This parameter mi has a lot of interesting property, well, not parameter, the presence of this logarithmic barrier, the presence of the parameter mi helps us to interpret, for example, things like duality gap. It's just proportional to the barrier term mi. There is also a uniquely defined point, a point solving these optimality conditions for any value of parameter mi. And all the solutions, if you go with mi, start at mi equal to infinity and go with mi to 0, then this will define so-called primal dual central trajectory, the set of all these points. It's, in case of linear programming, it's a continuous curve that takes us from very far away from optimality to optimality. Interior point methods follow this path and try to maintain points which will be feasible algorithms. try to do it. Keep primal and dual feasibility, and also attempt to stay close to satisfying this perturbed complementarity condition. When I say try to be close, it can be captured, for example, by the Euclidean norm, asking for Euclidean norm of the error in this equation to be bounded by a term which is proportional to the barrier term me. And this, as long as we really maintain such features, that is, all the iterates stay in such a small neighborhood of the central path, and we try to do small reductions of the barrier term from iteration k to iteration k plus 1, small reductions, meaning by a parameter sigma, which is very close to 1, as you can see, 1 minus a tiny fraction divided by square root of n, then we will be able to demonstrate that already after square root of iterations, a systematic decrease will give us a noticeable reduction in the duality gap. And after the number of iterations proportional to the square root of n, we will obtain arbitrarily large reduction, meaning we can get the duality gap to arbitrarily small value. In other words, we will achieve convergence. And without being very precise, this means that interior point methods enjoy this iteration complexity of O of square root of n, meaning that after the number of iterations proportional to the square root of n, an optimal solution will be found. IPMs have beautiful extensions. Two slightly later developed ones are the second order cone programming problems and semi-definite programming problems. And of course, there were earlier developed extensions from linear programming to quadratic programming and non-linear programming. But they are always based on this clever use of logarithmic function, which is very well suited to handle inequalities, to mimic, to replace inequalities. So for example, if you have a quadratic cone, which is defined here, we want to satisfy this inequality, t squared greater than or equal the norm of x, then instead of satisfying this inequality, we may penalize for approaching dangerously close to 0 with this inequality. And this would mean we penalize for the logarithm of a difference of these two sides, as you can see here. Very similar thing happens for SDP. SDP is much more complicated, as certainly Henry would have told you already. So in SDP, in semi-definite programming, we have an object which is a positive semi-definite matrix. But in this case, we can also define a logarithmic barrier function. This time, we will take the logarithm of the determinant of the matrix. And you can see the analogy. In case of the determinant of the matrix, the determinant is equal to the product of eigenvalues. But what is the logarithm of the product of eigenvalues? It's a sum of logarithms of eigenvalues. And here you see it's exactly the same object as in case of LP. Before I finish this brief introduction to interior point methods, I would like to comment on the computational perspective of it. Well, at the heart of interior point methods, there is always Newton method, a method well suited to solve nonlinear equations. So whenever we formulate first order optimality conditions, like in linear programming, this was the system of optimality conditions, we will apply Newton method to find a point which approximates the solution of it. And applying Newton method means computing the Jacobian of this function here on the left-hand side times Newton direction is equal to the current violation of this nonlinear system. In case of linear programming, the first two equations were linear, only the third one was bilinear, so it's not a heavily nonlinear, it's just mildly nonlinear system. And the differentiation would give us something very nice and easy. In more elaborate optimization problems, these systems may get noticeably more complicated than here. But what joins them all, at least in case of linear, quadratic, and non-linear programming, is that they always will have such a structure, which is a very well studied system of linear equations, which is at the origin of almost any computational linear algebra, I would say. PDE community, partial differential equations community, knows it under the name saddle point systems. We tend to refer to them as reduced KKT systems in optimization community. So to summarize this brief introduction, interior point methods delivered a unified view of optimization, starting from linear programming via quadratic to non-linear programming, and also the extensions to second order cone programs and semi-definite programs. They have enjoyably predictable behavior. They always solve problems in something like 20, occasionally 30 iterations. And they have unequal efficiency, really. For small problems, they are certainly competitive, but the larger the problems become, the more beyond competition IPMs become. It's possible to push things far. It's possible to solve problems of dimension 10 power 9. This was done already 16 years ago, but probably you could go much, much further than that with today's computers. Now I'd like to address some of the possible improvements of this basic methodology. So obviously, interior point methods heavily rely on Newton method, on Newton direction for the barrier problem. And for many years, these linear systems were solved exactly. However, it's possible also to use an inexact Newton method. After all, why should we solve the systems exactly, knowing that optimality conditions for the barrier problem are anyway not our ultimate goal? They are just a tool to make step to get closer to the solution of the optimization problem. And indeed, the use of inexact Newton method, which is very well studied in the general context of nonlinear equations, has also been brought quickly as an option inside in the context of interior point methods. This was done by Stefania Bellavia in '98. In this context, the main tool is to replace the exact Newton direction with the inexact one. And this inexact one would admit certain error in this equation. And the general theory says that as long as this error is only a fraction of the right-hand side, inexact Newton method is almost as good as the exact one. Well, based on this positive perspective on it, we'd like to be daring and use them in interior point method. That is, replace the exact Newton method with the inexact one. This raises theoretical questions as well as practical ones. So in terms of theoretical questions, I did the analysis of what will happen if you use small neighborhood, the so-called N2 neighborhood induced by norm 2, by the Euclidean norm. And it turns out that you can be very daring. You can actually accept up to 30% error in the direction, and this will not affect the worst case complexity. In more practical symmetric neighborhood, which is a much wider neighborhood and therefore much more attractive for practical usage, one has to be a little bit more cautious, but still up to 5% error in the direction. So up to 5% of inexactness does not have any impact on the worst case complexity, which is certainly a very encouraging theoretical result, which allows us to go for inexact Newton method in this context. I think at this point it's worth mentioning that interior point methods have an amazing ability of handling inequalities. Inequalities are difficult in optimization. Equations are easy. Equations, you know what you have to do with an equation. You have to satisfy it. However, an inequality is really a full interval, and you never know whether inequality will be active, that is satisfied as an equation on the boundary of inequality, or will it be satisfied as a strict inequality, in which case you could dispose it. Whether it is present or not, it doesn't really matter for the optimization problem. And an overarching feature of interior point methods is an incredible ability of finding these inequalities which are important, finding the essential subspace of the problem where the optimal solution is really hidden. By the way, may I say that if anybody has questions in the middle of my talk that I absolutely do not mind, you can ask them. We've just finished part one of it, because now I'd like to take you through a journey of things which are beyond the obvious interior point method tricks. And I have 4 items to cover, 4 little contributions to mention. So first of all, I'd like to talk about how much...
I have a question. Yes, sir. When you say inexact, do you mean inexact for the entire Newton equation, the entire big system, the optimality conditions?
My analysis, the one that I referred to, applied to feasible method. So in case of feasible method, I assumed that the primal and dual feasibility was assumed, so there was no inexactness there. In such case, inexactness only applied to complementarity condition.
Okay, thank you.
But it's just a technicality. One can develop an inexact method which allows inexactness everywhere. I just picked up an easier model, the feasible method. Have I answered your question?
Yes, thank you.
Okay, right. So coming back to this, beyond the obvious, I'd like to draw your attention to the fact that we can relax significantly the rigid structure of interior point, and then the question will be how much of this methodology really has to be maintained and which elements of it could be relaxed. Here in the second item, I'd like to show you that a lot can be relaxed. We can use an inexact to the square interior point method, where inexactness will be almost everywhere, will be an overwhelming feature of it, and still interior point methods for some easier problems converge beautifully fast and are very attractive. I also would like to mention a joint work with Kimonas Fontulakis, who, by the way, now is a professor at Waterloo University, on primal dual Newton conjugate gradient method. And the very last thing developed only this year, the variety of sparse approximations with interior point methods. So let's talk about this relaxed interior point method. And here I'll step into a difficult case of problem, that is semi-definite programming problem. They still remain a challenge, and this is because linear algebra in SDP is significantly more complicated than in the other classes of problems. To cut long story short, linear algebra of SDP, the problem of dimension n, requires solving linear systems of dimension n squared by n squared, which obviously is a tough task. So our aim here was to redesign interior point methods for SDP, and of course replace exact Newton with inexact one, do everything in a matrix-free regime, and also make sure that we use as little memory as possible. Ideally, the properly limited memory, work in properly limited memory regime. in this context, of course, linear systems have to be solved by Krylov methods, and the appropriate choice of the preconditioner is also very important. So let's have a look at SDP. This is the SDP in the primal form and in the dual form. And let us make this assumption that the matrix S is sparse. It may be sparse because it is a union of very sparse matrices AI. Many relaxations of combinatorial optimization problems, for example, contribute here matrices AI which have 1 or 2 or 4 non-zero entries. So even if there are quite a few of them, their aggregation, the merging of the sparsity pattern still maintains as pretty sparse, and the sparsity should be exploited. Optimality conditions for general SDP can be written in this way, although the more typical way of writing them would be that this last equation would be written as capital X times capital S is equal to me times identity. Here I want to underline that here capital X is a general positive semi-definite matrix, so is capital S. So these are not diagonal matrices like in LP. These are general positive semi-definite matrices. And but I would like to draw your attention to this equation, X minus me S inverse, because it illustrates certain important feature of sparse matrices. Although the matrix S may be very sparse, its inverse is frequently a completely dense matrix, which means that it would be very unwise to have to store explicitly matrix X. And this is one of the arguments that working with the dual barrier problem, which does not make X appear explicitly here, might be an attractive option. If we want to use this dual path following IPM, we will do it in the following way. We will use the same philosophy as interior point. However, we will make much more brutal reductions of the barrier term. Just the new barrier will be the previous barrier term times sigma. And rather than strictly following the path, we will make jumps from one point close to the path to another point close to the path, accepting the fact of having to do more Newton iterations. So Newton iterations will be done on this nonlinear system, and they will continue until the scaled Newton step in variable S, you can see pre-scaled and post-scaled by the current value of dual variable S, is small. Small understood in terms of Frobenius norm. So the moment the Frobenius norm on the Newton step on S becomes small, we know we have approached sufficiently well the point on the central path. This approach is attractive. It can solve certain semi-definite programming problems without necessarily explicitly using matrix X. So it's very well suited for problems where S is very sparse, as these two papers demonstrate in more detail. My second example deals with this very inexact interior point method. So let me remind you that a standard inexact Newton method admits certain residual, certain error, capital R here, and requires that this error should be, the norm of this error should be bounded by a fraction times the right-hand side term, where the fraction should be, well, any number between 0 and 1. This is enough to study convergence of the general inexact Newton method. But even such a condition, when I looked at it very closely, turns out to be disappointingly conservative. Let me just show you the following thing. if you deal with linear optimization, in which Newton's system has this form, so the Jacobian of first order conditions times Newton direction is equal to the current infeasibilities, current violation of optimality conditions, then should we be lucky and do full Newton step with alpha equal to 1, we will immediately absorb these linear terms. We will reach primal feasibility and dual feasibility, and we will also nicely reduce the complementarity. But in practice, such steps happen very rarely. It would be a dream of any optimizer to have step sizes equal to 1, which almost means finding the optimal solution in just one shot. So if we are prepared to do more iterations, why should we waste time on computing an exact solution of the system? We should admit, we should accept considerable errors in this system of equations. And let me share with you an intriguing observation. This is what happens at a particular interior point iteration. The pictures that are displayed for you are the following. The first one shows the evolution of error in the conjugate gradient method. It non-monotonically decreases. You see the tendency is to decrease. CG is not monotonically reducing the residual, so occasionally there are little jumps. But after 20 iterations, we reach the accuracy 10 power minus 3. After 60 iterations, we reach the accuracy 10 power minus 6. However, this is just a linear algebra perspective on solving the linear equation system, the Newton system. While at the same time, we looked what happened to the infeasibility with the same evolution of iterations from 0 to 60, what happened to complementarity and what happened to primal and dual step sizes. And as you can see, after about 15 iterations, infeasibility has been reduced and it will not be reduced anymore, whether we get more accurate direction or not. The same happens with complementarity. Complementarity has been reduced, and after about 20 iterations, we will not get any more improvement in it. We will only waste 40 more conjugate gradient iterations. The same with step sizes. They stabilize after about 15 or 16 iterations. So what's the point? Why should we do 4 times more or 3 times more iterations getting here while we actually could have stopped at this point and enjoy already a very constructive Newton direction and making a significant progress in interior point method? Well, this was the computational observation, but actually we can convert it into a piece of rigorous theory. We can accept the direction produced by inner solver. By inner solver, I mean the linear algebra solver, as soon as those conditions are satisfied, meaning the step, Newton step in X compared with the variable is not too large, Newton step in S compared with the variable is not too large, and we already achieved some reduction of primal infeasibility and dual infeasibility. We have implemented this technique either with both, with conjugate gradient and with mean res, depending on whether we solve normal equations or augmented system. And we've observed that it really reduces the number of linear iterations by 70 to 90% of iterations. And this usually translates into something like 60 to 80% reduction of the overall CPU time for interior point method. The negative side of it is that we lose something in terms of complexity. Complexity drops by an order n, from O of n to O of n squared. But, well, that's the worst case complexity. It's weaker, it's poorer, but from computational point of view, the method works better, is faster. There are details in the report. On this graph, I'm just showing you what would happen if we used a standard a standard stopping criterion for conjugate gradient, which would ask always to find a very precise solution to the linear system with a 6-digit accurate solution. Well, this would mean that at some initial iterations of interior point, we would have to do as many as 400, 500 conjugate gradient iterations. While we know very well that we are so far away from optimality, then going for accurate solutions in the Newton system is just waste of energy, waste of time. You would say immediately, well, we do not have to go to 10 power minus 6, but then the question is, so what should be this precision? And there is no good answer to this. That's why we wanted to design completely new stopping criteria, which would give us this uniform behavior. This yellow line, this is interior point conjugate gradient, the new way of the new stopping criterion for the CG method, which always keeps the number of iterations to its minimum, well, about 50 almost through the whole solution process. This was used in particular in a very interesting problem, which requires a separation of materials in X-ray tomography. The interest in this problem came from physicists working in Helsinki who wanted to use this interesting looking regularizer, which you reveal immediately gives us an indefinite matrix and therefore non-convex term added to the function. So this is the least squares problem, non-negative least squares problem, in which there is a Tikhonov regularization on X, and on top of it, there is this extra inner product regularization, which, considering the fact that X is non-negative, means that the scalar product between variables corresponding to material 1 and material 2 should be as small as possible. This is the material separation, as image processing people explained to me. We applied this new method, this interior point conjugate gradient, and we could really see significant reductions. You see here 25,000 CG iterations with a standard stopping criterion, 2,600 overall iterations in this more intelligent conjugate gradient, more intelligent stopping criterion. And of course, the clear gain in the solution time, 600 seconds as opposed to 5,000 seconds. So 8 times faster. For CPU time, about 10 times fewer iterations. Right. And I'll go to a different application. This one originated from big data optimization and the whole buzz about machine learning, doing classifications and computational statistics, and lots of signal and image processing applications. All those problems, but not all, but many of those problems can be represented as a large, possibly dense quadratic programming problem. But in these problems, there is a regularizer often added, and I'd like to illustrate the difference between regularizer which involves norm 1 and regularizer which involves norm 2. So that's a case of binary classification. You would like to find a separation between one cluster of points and another cluster of points. And if you use norm 1, then you will promote as few you would promote the solution which involves as few components of vector x as possible. If you use norm 2, you try to spread the error uniformly between all the components. So in this case, just one component, component A1, is enough to separate the data points. In this case, both A1 and A2 will be used to do the separation. And you probably think, what on earth is he talking about? What is the difference? Of course, the difference in dimension 2 is irrelevant. But if we talk about a dimension of 2 billion, then we would like to have 1,000 or a few thousand non-zero entries rather than full 2 billion of non-zero entries promoted by this by this Euclidean norm. So there is a genuine interest in using L1 regularization in computational statistics, in machine learning, in image processing. That's the problem. We have to minimize the function. It could be just the least squares, but we want to promote sparsity in X. And when optimizer looks at such a problem, well, the striking thing is that, well, it should be easy. There are no constraints here. So problems without constraints are usually chapter 1 of any book on optimization. But there is a little bit of a difficulty. This is the norm 1, which is non-differentiable. So you immediately say bye-bye to gradient, to well, Hessian or any other higher order information. So we'd like to overcome this restriction imposed by norm 1. This can be done, for example, by splitting the variable x into positive and negative parts, and that way replacing the absolute value of x, of the component of x, by the difference, well, the absolute value by the sum of those two terms. Another option is to use some kind of smoothing, which would replace the cask with a smooth function. I'll show you this Huber regularization or pseudo-Huber regularization. This is a zoomed picture in which the blue line indicates the cask, the absolute value of x, while the green dashed line shows the graph of the pseudo-Huber function. You see it agrees pretty much with the blue line far away from 0, close to 0. It just smoothly replaces the cask with something which looks pretty much like a quadratic function. Well, this leads me to a generalization of interior point method, which looks at the interior point as a continuation, as a homotopy approach. What happens in interior point methods is that we replace a problem with a sequence of problems with gradually reduced barrier term me. And we could generalize this procedure to say that, well, the same could be used with, for example, pseudo-Huber regression. That is, replace absolute value of the variable with this pseudo-Huber function and gradually reduce this parameter me from a large value to a smaller value to get to improve the quality of the approximation. Well, whenever you see such a thing, there are two questions. Would the theory allow it? Would it work in practice? But you probably know that a lecturer, a speaker will not put questions on one slide if there was no answer on the following slide. So yeah, that's what we can do. Let's take a specific example of compressed sensing, and let's apply this continuation technique. In compressed sensing, we try to find the minimum of least squares, and on top of it, the vector x should be such that in certain space controlled by this matrix W, it will give us a sparse solution. This means in certain dictionary, the signal x should be sparse. In certain space, it should be sparse. Well, this is norm 1, which is a troublemaker, so we will replace it with pseudo-Huber function. And now the question appears, well, that's the true solution we would like to find, x tau. If we use the pseudo-Huber function, we will find a different solution. The question is, how big an error will we make between this solution and that one? And there is a theoretical argument to say not such a big one, because we can generate a short sequence of quickly decreasing values of this parameter in the pseudo-Huber function. And the solutions obtained by these approximate problems, which use pseudo-Huber function, are not far away from the true problem from the true solution x tau. Again, This has been studied both from theoretical point of view and from the practical point of view, leading to specific preconditioner that can be used in this context. By the way, when we worked on it with Kimonas Fontulakis, we also realized that these problems, the L1 regularized least squares, appear nowadays in so many applications, and also there are so many algorithms dedicated, specialized for solving such problems, that it would be good to have some kind of systematic way of comparing these algorithms. So Kimonas developed this generator for problems where the matrix A can be fully controlled by the user. It is determined by singular value decomposition, and we can control the matrices U and V because they are a sequence of products of Gibbons rotations. So that way we can easily control the condition number of A by choosing element sigma, and the sparsity of matrix A by choosing how many Gibbons rotations will be here hidden in matrices U and V. This is a MATLAB development, so anybody interested can use the code. But then we performed excessive computational tests, which overall took 4 months of CPU running, and we compared several methods for optimization: FISTA, parallel coordinate descent method, also this projected scaled subgradient, and our primal dual Newton conjugate method, Newton conjugate gradient, sorry, primal dual Newton conjugate gradient. So what we could observe is that those 3 first-order methods work really amazingly well as long as the condition number of the matrix is small. When condition number starts to grow, they start to struggle. When condition number grows further, they usually just stall completely and cannot converge. Second order method, on the other hand, with rather simple diagonal preconditioner, could go much further, could deal with problems with noticeably larger condition number. If you ask me what to do for more ill-conditioned problems, the answer would be, of course, well, we need something more elaborate than just a diagonal preconditioner. We would need a preconditioner that understands better the spectral properties of the matrix A. And we also run tests on really very large problems using high-performance computer. This is an Archer, the computer which in March 2015, so when the computations were done, was ranked 25 on top 500 list, but probably now it would surprise me if it was still in top 100, probably is somewhere beyond top 100. It's a powerful machine. It has a lot of teraflops per second and a lot of memory. This allowed us to solve problems which start from 1 billion and go to 1 trillion of variables. Every time we increase the number of problems by a factor of 4, we increase the number of processors by a factor of 4. No surprise, the memory increases by a factor of 4, but look at the time stays the same, which reveals almost perfect scalability of the method. Indeed, when you think of conjugate gradient is doing what? It's doing matrix vector product. Matrix vector product can be parallelized to perfection. You have more processors, you do it faster. That's it. That's why there is practically perfect scalability of the approach of the primal dual Newton conjugate gradient method on such problems. Finally, I'd like to talk about other sparse approximations, and I just have one last example here. There are lots of problems in which you have several sparsity promoting terms added. Sparsity on vector X and maybe sparsity in some other space, in a transformed vector X, linearly transformed vector X. We dealt with several applications of this type: sparse portfolio selection, classification models with functional magnetic resonance, total variation-based Poisson image restoration, or linear classification, the typical machine learning trick. So that's a new work finished only in February this year. I'll show you just one example, this functional magnetic resonance imaging, because here we performed the comparison of interior point method with FISTA and ADMM, two very fashionable first-order methods. And we report here three features, three characteristics: classification accuracy, corrected pairwise overlap, and the solution density. Don't forget, we look for sparse solutions, so we'd like the density to be as small as possible. But with those two parameters, we would like them to be as close to 100% accuracy as possible. So we want ACC large, we want corrected overlap large, we want small density. And look what happens. When interior point is used, it can, for certain parameters tau, really develop perfect sparsity. FISTA can do it for some parameters, not for the others. ADMM, well, actually can never produce sparse solutions. It would really have to run for years probably to do it. But as far as the other parameters are concerned, FISTA struggles with this corrected overlap, cannot really match what is delivered by interior point. So it's just good to realize that although interior point methods require a serious investment, require significant computational effort per iteration, then they eventually deliver a very high quality solutions. And you can see this very well on this picture, which shows the evolution of all those three parameters: accuracy, corrected overlap, and density, how it changes. So interior point spends about 10 minutes without doing much, but after about 10 minutes shoots quickly to almost perfect sparsity, to the minimum. Look what FISTA is doing. FISTA starts almost immediately after 2 minutes, has already a good idea of sparsity, but will never ever reach this level of sparsity. It would take not 60 minutes, believe me, it would take much longer for it to get to the same sparsity of solutions. So I think many people just use first-order methods because they want to stop them earlier, and in some applications that's good enough, but not in all applications. This was my last technical slide. It takes me to conclusions. Well, undoubtedly, interior point methods have delivered a revolution to optimization. Although they are second-order methods, they are very competitive. The second-order information does not have to be exploited with full accuracy. Sometimes very little of second-order information is enough, through the notions of inexact Newton method, which makes also matrix reimplementations possible. The tricks important to remember from interior point is that the method is very good in detecting where the optimal solution is hidden. They are good in detecting the essential linear subspace in which the solution resides. And they can be specialized by exploiting linear algebra, so they can work for those well-studied classes of problems like LP, QP, second-order cone programming, and SDP, but they also can be generalized to L1 regularization and the other problems which originate from sparse approximation applications. This really brings me to the last slide. Thank you very much for your attention, and I hope you will all stay safe and healthy. Thank you.
Okay, thank you very much, Jacek, for a very interesting talk and lots of information about the theory behind it and of course the implementation and sort of I guess it's the latest information on what the latest software can do. So I would like to ask people for questions, and I think if you don't mind, we can go longer and start this next talk a little bit later and treat this sort of like a bit of a workshop. So hopefully, please ask questions.
Hi, Jacek.
Yes.
Hi. When you showed those strong scaling results, what were those with dense matrices you were multiplying?
Some of them have dense blocks. For example, this functional magnetic resonance imaging is a very large matrix, but there is a noticeable, say, kernel information which actually is dense. If I remember correctly, you would have something like maybe 5,000 dense rows in a problem that is maybe 20,000, has maybe 20,000 constraints.
Okay, all right.
But,
yeah, I have an idea I want to discuss with you, but we do it offline.
Okay.
But, yeah.
Okay, anybody else? Well, I don't want to dominate, but I'll ask a question if you don't mind. So when you're working on the inexact problem, this sort of goes to my question that I asked already. And you said that, okay, you can change things and not assume primal dual feasibility. But are you working on the normal equations or something like the normal equations when you're applying the inexact method, or are you treating the theory on the original optimality conditions?
The theory was really dealing with the optimality conditions. So the theory dealt with inexactness and allowed inexactness in a specific equation. If you would like to have inexactness in the other equations, inexactness in the dual is easy because there is this identity matrix. The dual for LP is A transpose Y plus S is equal to C. So you can absorb a lot of error inside S. Okay, almost any error in Y. It's not always that flexible, not in every optimization problem, but
in the implementation, are you doing the inexact method on the normal equation or on the?
Not necessarily, depending on application. We always look at what is best for a given application. It can be on normal equations. It can be on augmented system. Then instead of CG, we would use MinRes. And still in MinRes, there are also ways of incorporating inexactness, stopping MinRes earlier. But one could also anticipate working with a full 3x3 block, although I haven't implemented it that way. We don't have any implementation. It's one of the things that I actually asked Filippo Zanetti, my PhD student, to look closer into, because the system potentially may have even more flexibility. But to answer shortly your question, we work either with normal equations or with augmented system, either with CG for normal equations or MinRes for augmented system.
Thank you. Anybody else?
I would like to ask one question. What's your take on like continuous versus discrete variables? And
say again, you want to have discrete variables. Did I?
Yes, and so I think yes.
Well, interior point methods are, of course, methods for continuous optimization. So the only hope that I would see in this context is that if you have a quality relaxation of your combinatorial optimization problem, and you probably know that, for example, SDP relaxations for max cut have a nice guarantee of not being too far away from optimality. There are some attractive SDP relaxations of quadratic assignment problems, and I believe of many other. Then yes, you can solve the relaxation, but how to jump from a solution of a relaxation or a solution of an approximation to integer solution is beyond me. I wish I could say it's doable, but I think there's a lot of art required to do it in an intelligent way. I certainly don't know how to do it.
You mentioned somewhere about subgradient methods, maybe.
So if you use subgradient methods, if you use, for example, cutting plane methods, then yes, oh, absolutely. Then I can talk for another hour. So just be careful with asking such question. But yes, interior point methods have a lot to offer, because if you use cutting plane methods, then rather than adding one cut at a time and struggle with the simplex method, it's much better to solve the restricted master problems with interior point, because then you are staying in the interior of the polytope, and you are significantly less affected by specific cuts that are added to it. So that's a big piece of theory, well studied and very attractive computationally. It's something that I didn't mention it here, but I developed a very powerful methodology like this with my other two PhD students, Pablo Gonzalez and Pedro Munari, in a sequence of papers. You can find them on my website.
Thank you. Any other questions?
Okay, I have. Okay, you please. Okay, I have a question. Could you please give some comments on the factorization-based precondition? For example, for precondition CG. I mean the LU decomposition and the Regularization. I mean how to balance this. I mean.
I'm sorry. Would you mind repeating the question?
Sure. Thank you very much. I mean, for preconditional conjugate gradient, you mentioned that the factorization-based method should be a good choice. For example, the LU decomposition or Cholesky decomposition. But normally, it's very basic. I mean, how to balance the computing effort for the precondition.
I don't really know.
Right. So I think you're asking me about preconditioners. Preconditioners have generally formulated objective as capturing the spectral properties of the matrix, and preconditioners usually depend on the specific application and the specific features of the matrix. So one general approach is some kind of incomplete Cholesky factorization for normal equations could be a preconditioner. But I have to say, this is a rather, generally speaking, this is not a good preconditioner. It's a preconditioner. Yes, I agree. If you don't know anything better, you could use it, but it's a very black box approach. And if you know something more about the problem, then you might be able to develop much more sophisticated preconditioners and cut down the number of CG iterations significantly.
Okay, thank you very much.
Thank you.
I have a quick question, Henry, if possible.
Yes, well.
Okay, so Jacek, thank you so much for the interesting presentation. When you compare the FISTA, the ADMM, and the method, the interior point method, it was clear, and this was your comment, that FISTA or ADMM would get you to would perform a bit faster at the beginning, but then they will never get you to the required sparsity. Have you tried mixing both, so starting with the FISTA or ADMM to get you closer to a nicer solution, then apply interior point method, something like that?
No, we haven't tried. One of the difficulties with such an approach is that interior point method, I do not want to say cannot warm start, because I always say just the opposite. Yes, they can, but they can warm start from points which do take interior point mentality very seriously. That is, they can warm start from points which do have certain centrality properties. The starting points, like the ones, for example, originating from ADMM or from FISTA, would not have such features, which means that they will be advanced. You are absolutely right. They would be closer to optimality, but it's very difficult to translate them as good initial points for IPM.
I see. I see. Okay. Thank you.
Okay, thank you. Anybody else? So maybe I have one question. Hopefully it's quick and short. When your comment about step one, step equal one, length equal one. So you said that this hardly ever happens. I think it hardly ever happens because of the choice of the sigma in these predictor corrector methods.
Yeah,
it's just too aggressive. Have you given any thought to, or I don't know, has anybody, because it's so nice to have step length equal one, because then you know forever after you do have exact feasibility. Is it worthwhile?
I would have mixed feelings about it. The reason for that is that sometimes not having perfect primal feasibility and perfect primal dual feasibility actually leaves us with more room to maneuver. So I can imagine situations in which it would be very welcome to obtain perfect primal feasibility and perfect dual feasibility early enough, and then only continue the struggle to reduce complementarity. But I can also imagine situations which are just the opposite, that if we force ourselves to be primal and dual feasible, we will significantly restrict the area to maneuver, and we will have to do quite a few interior point iterations. So tricky question. No easy one way or another answer. Henry.
Thank you. Anybody else? Okay, and in that case, thank you again for a very nice talk and all the nice questions and answers.